All right. So in this particular case, we want to establish this proof. So let's look at that. So proof. Right. So of course, observe that the sample space can be decomposed into mutually exclusive events. A and A prime. We can observe that the omega can be reconstituted as A union A prime, right? And this makes sense. Once you take an event and you take the union of that, all right, because think about it. A is, the event, and A prime is another way of saying, I think I wrote it here. A prime is another way of writing the sample space without A. Okay, so the sample space without A, union A, would give you the sample space. Okay, that's the whole idea. So at this point, this implies that when we take the probabilities of both sides, right, the probability of the omega would be equal to the probability of A union A prime. And you recall that the probability, I think this was theorem 1. Or we may establish that later on. So since the probability of the null set, okay, is 0, we know that the probability of omega is 1. And you can easily show this, right? So it means that this entire probability is equal to 1. All right. In other words, you'll see that because the A and B, because the A and then the A prime are mutually exclusive, we can apply axiom 3 or the special additive law, right? So this is actually equal to probability of A plus probability of A prime. And we know that the probability of the omega is 1. There's a certainty there. So this implies that 1 is equal to this. And this further implies that the probability of A prime is 1 minus the probability of A. All right, we'll take a few more theorems and then we'll switch to another concept. So theorem 6. So theorem. So there's a 6. So if A and B are events defined on omega, and if A has this relationship with B, then the probability of A is less than or equal to the probability of B. Now, notationally, this is very important. Keep in mind that A and B are events. They are not numbers. Even if they are events containing numbers, they are sets, so they are events. So we cannot say that A is less than or equal to B. That will not be correct to say. In the same way, the probability of A and probability of B, they are numbers, they are not sets. So we cannot say the probability of A is a subset of the probability of B. No. For numbers, we can use an equality, and then for sets, we can use the subset notation or relationship. So proof. Observe that So once again, let's always try to visualize this. Right? So you have this case where you have your B and then you have your A. But of course, A can be equal to B, right? But we just want to visualize it well. And of course, this is your sample space. Right? So observe. Observe that B can be decomposed into two mutually exclusive events. As so think about it. We can say that B is equal to A union B intersection A prime. Let's look at this closely. We know that B is what? The biggest set and every element within it. All right. Good. So that's our target. Now, we know that A is the entire inner circle. So we need something else to add on to A in order to arrive at the full circle B. Now let's take a look at this expression, B intersection A prime. What is A prime? A prime would be what? Members of the sample space that are not contained within A. All right. So A prime would be every other element that lies outside of the A. And every element that lies outside of the A intersection B would give you this region. All right. So you would see that this region, okay, so B intersection A prime, which is that outer region, B intersection A prime union this A would give you the whole of B. That's the whole idea. And so the set B can be decomposed into some mutually disjoint, mutually exclusive events A and then B intersection A prime, right? And because these two events are mutually exclusive, it means that we can apply our axiom 3. All right, so since A since A intersection B intersection A prime is empty. Okay, they are disjoints. It holds. By theorem, what theorem is this? Yeah, by theorem 3. By theorem 3. Which is a special addition law, which is also the axiom 3 of probability. That's the probability of both sides, right? So the probability of B will be equal to the probability of A plus the probability of B intersection A. And if you look at this very well, this probability B, okay, has been rewritten as the sum of these two, the sum of the probabilities of these two disjoint events. Okay, what that means is that if you recall, or if you observe, the probability of B intersection A prime is a legitimate probability, meaning that it would always be non-negative, which simply means that it will be greater than or exceeds 0, right? Now, if you have two values, let's say you have some values, x is equal to y plus z, and this z is greater than or equal to 0. What does it mean? This means that x would be greater than or equal to y. That's the implication. So if the probability of B is equal to the probability of A plus the probability of B intersection A prime, then it means that we can infer that this will be greater than or equal to
you have to get a lot of people
the probability of A. Okay, the reason is, right? The reason is the sense, and the reason is this.
We are going to be.
The reason is since,
Like the person is done. Not you telling the products.
since this probability, okay, so since, I don't know if I can write it somewhere, but since the probability of A, okay, I don't think I have much space there, but the whole idea is that because the probability of B intersection A prime is greater than or equal to 0, then this entire expression will be greater than or equal to A. So I can say that it holds by theorem 3 or special additive law or axiom 3 that okay, this expression holds. And this is because since the probability of B intersection A prime would always be non-negative. Let's take one final theorem and then we'll talk about independence. I mean, conditionality. So this is theorem 7.
How is that for?
So the probability of occurrence of at least one of two events all right, let's say A, B. Never exceeds the sum of the probabilities of the events. And this is what exactly we mean by that. So the probability of A union B, right, would always be less than or equal to the sum And this is sometimes called the Boole Inequality. So it depends on the text that you're reviewing. So we have Boolean algebra. I mean, Boole has is one of the names that you'll come across, in due course of time. So here the proof is very trivial, right? So the proof right? So, I mean, just going back to this expression, what we just looked at, all right? The probability of B is equal to the probability of A plus the probability of B intersection A prime would always be greater than or equal to the probability of A, right? So, I mean, since the results would just follow, right? So let me just make a quick remark here. The results follow. Or the results, singular. The result follows from I think theorem 2. Yes, the general additive law, right? It's coming from here. Since the probability of the intersection, all right, would always be greater than or equal to 0, it means that then the probability of A union B would always be less than or equal to the probability of A plus the probability of B. In other words, since the right-hand side would always be greater than or equal to 0, then it means that the right-hand side would exceed or be equal to the probability of A union B. So the result follows from the results follow from theorem 2. And there's the general additive law. General addition law. Right, the results follow from the general addition law or theorem 2. Since all right? And of course, we can extend this. We can extend this corollary. We can extend this theorem, actually. That's what I mean to say. Right? We can say that so for three events, A, B, C, right? The probability of A union B union C would always be less than or equal to the probability of A plus the probability of B plus the probability of C. All right. And then in the end case, so corollary corollary 7.2, right? The probability of A1. So if you have events, so for events, A1, A2, AN, right? The probability of A1 union A2 union AN, okay, would be less than or equal to the probability of A1 okay, up to the probability of AN. So, I mean, or simply, we can say that the probability of right will be less than or equal to the sum. All right. The only time that this equality is either an inequality. Okay, so far we've been looking at inequalities. All right, inequalities, and then inequality here. The only time the left-hand side will be exactly equal to the right-hand side is when the pairs, I mean, each pair is mutually exclusive. right? All these are coming from the general additive law. And in the general addition law, the events there may be overlaps, right? So we're saying that if there are overlaps, then you would have less than, okay, the sum of the probabilities, the sum of the unions of the events is going to be less than the sum of the individual probabilities. But the equality would only hold when you have any of the events, okay, when you have each pair of the events being mutually exclusive. All right, so just a quick recap of the core ideas that we've considered today. We've been looking at the probability laws and theorems, and there are quite a number of them. What we're considering, or what we've considered today, are parts of the fundamental laws. There are fundamental laws, there are some intermediate laws, and we have more advanced laws as you progress with your studies in statistics, or mathematical statistics for that matter. So we've considered the first theorem, which is the trivial case of the probability of the null set being zero. And I've explained the intuition behind that the null set characterizes impossibility. And when we say the probability of the null set is zero, it's simply telling us that really it's impossible because the null set does not contain any member, whereas the sample space contains all the possible outcomes that you can observe. So it's just a way of saying that, I mean, an impossibility happens when the probability of a particular outcome is zero, right? So this is how the proof goes. Theorem 2 is the general additive law, which is an extension or a generalization of axiom 3. So we're considering the case where the two sets or the two events A and B may overlap. The case where the two events have some commonalities. So in that case, we've looked at establishing that property, and we're saying that in the case where the intersection is not null, then the probability of the union would be the probability, the sum of the individual probabilities less the probabilities of their intersection, right? And of course, if the intersections is the empty set, then the probability of that intersection will be zero. And it means that brings us back to the axiom 3, which is really the special addition law. So we can generalize this general addition law by Corollary 2.1 and then Corollary 2.2 for the case of 3 case events, A, B, C, and then the n case event where you have some A1, A2, all the way to AN. And I've given you sketches of the proof. So this is a corollary. We're saying that for mutually exclusive events, then axiom 3, which is the special addition law on the left-hand side, theorem 3, can be extended to the n case. So the probability of n union of sets or events is the same as the sum of the probabilities of those n events or sets. We've also said that what happens if A is a containment or can be equal to another set B? The result here is that the probability of the union of A and B will just be the probability of the bigger set B, right? We've established how this comes about. We've also considered the law of complementation, right? The idea that the probability of having or observing an event, say A prime, is basically 1 minus the probability of the event A. And I explained that A prime or A complement can be thought of as the sample space without A. So by definition, A prime is all members within the sample space that are not in A. That's the complement of A. And we've established the proof as well. And we've gone on to Theorem 6 that says that, once again, if you define these two events, A and B, over the same sample space, omega, and A is a subset of B, then the probability of A would always be less than or equal to the probability of B, which is also a very important theorem that complements some of the others that we've considered in the past maybe hour or so. And we look at Boole's theorem, which follows from the general additive theorem. And we've considered some corollaries or some possible extensions of this result. All right. And so in the next session, we would further our studies on some basic laws and theorems of probability. We'll be starting with the idea of conditionality, conditional probability, and we'll look at multiplicative laws and some other interesting concepts underneath probability. So thank you very much for your time and have a pleasant rest of the day.